they even have pronouns in this.
Good morning, everyone. Welcome to Stat Speaks, our colloquium on statistical sciences. I am George Manapat, a faculty member of the UP School of Statistics, and I will be your moderator for this colloquium. Before we begin our talk this morning, here are some reminders for the participants. You are requested to reserve your questions for the Q&A forum at the end of the presentation. You're also enjoined to use the raise hand feature of Zoom to facilitate the Q&A forum in an orderly manner. You may also use the chat feature of Zoom to relay your questions. You may send your questions to everyone or privately to me, your moderator. Now, whether asking the questions live, relaying it via the chat box, you are requested to use the following format when asking questions. First, kindly state your name, the university or institution or agency where you work or where you study, and then state your question. Without further ado, let us introduce our speaker this morning. Our speaker this morning is currently a faculty member at the UP School of Statistics. He obtained his bachelor's degree in statistics in 2010 and graduated magna cum laude. In 2014, he obtained his Master of Science in Statistics, also from the UP Diliman School of Statistics. He received his PhD statistics degree from the University of Maryland, Baltimore County, with a dissertation entitled Rectangular Statistical Regions with Applications in Laboratory Medicine and Calibration, under the supervision of Dr. Thomas Matthew. This work earned him the 2020 Outstanding Graduate Research in Statistics at UMBC. He also worked as a research fellow at the U.S. Food and Drug Administration and as a lecturer at UMBC. Our speaker received numerous research awards, including the 2021 American Statistical Association Biopharmaceutical Section Scholarship Award for notable research, academic achievement, and applied project work related to biopharmaceutical statistics, and third place in the poster competition of the 2020 American Statistical Association Biopharmaceutical Section Regulatory Industry Statistics Workshop. He has written numerous refereed journal articles and a recipient of various university and department awards, including the one UP Faculty Grant Award for 2016 to 2018. He is currently a member of the American Statistical Association, Institute of Mathematical Statistics, International Statistical Institute, Society of Industrial and Applied Mathematics, and Philippine Statistical Association, among others. Ladies and gentlemen, let us all welcome our speaker, Dr. Michael Daniel C. Lucagbo. A warm applause for Dr. Lucagbo.
Thank you, George. Good morning, everybody. And first of all, I'd like to thank the organizers of this colloquium headed by Dr. Imogen Evidente inviting me. I'm honored by this invitation. So let me now start to share with you my presentation, and hopefully you can already see it right now. My talk is entitled Fiducial Inference in Testing the Comparability of Originators and Biosimilars. Now, these terms might not be very familiar with you, so I'll be introducing this now as we go on, especially itong fiducial inference. Now, let me first introduce this biologics or biological products. These are large, complex molecules which are used for the prevention or treatment of a disease. Examples nitong mga biologics are these vaccines, blood products, allergenics. Now, these are different from just generic drugs, which are small molecule. Now, these are more difficult to handle and also more difficult to study. And if these biologics, no, usually yung originator, yung nauuna sa kanila, there is a patent that is attached to these biologics. And once that patent expires, then we can introduce new biologics. No, tawag natin doon ay biosimilar. So it is developed and approved as a comparable version of another biologic that is already available in the market. So parang maging competitor siya, or and it's equally effective. And that's what we have to establish. No, can we really say that its quality attributes are the same as that of the originator? Now, so I've already used the terms originators and biosimilar, but I will also be referring to them as reference and test product. In fact, I think throughout most of this talk, I will use the terms reference and test product more often. When we say reference product, or that's the originator, and we compare it with our test product for various quality attributes, no, for various kinds of criteria, itong equivalence, similarity, comparability, and magkakaiba to, no. I say they're equivalent, similarity, and comparability, but technically they have different meanings. And in today's talk, I will focus on the third one, itong comparability between originators and biosimilars, or between reference and test products. Now, in a test for comparability, we test if the quality elements of a test product falls with high percentage within the quality range of the reference product. In other words, kung titignan mo yung distribution ng test product, dapat pasok siya, no, within the range that is defined by the reference. And I have here an illustration coming from MIELKE et al. Suppose RQ and R1 minus Q are the reference quantiles, and you have here yung reference, yung nasa kaliwa, and distribution. I'll call that the reference distribution. And you already have the quantiles, the Q and 1 minus Q quantiles of the reference distribution. Now, what I'm going to do on the diagram now, as on the right, is I will superimpose those quantiles to the distribution of the test product. So ayan, naka-superimpose na siya dyan sa kanan. And the idea for comparability is that the area of the test distribution that's outside of those two quantiles, the total area there has to be small. Therefore, we want the red area and the blue area, if we sum them up, with that area has to be small para masabi natin na yung attributes ng test distribution ay pasok dun sa quality range defined by the reference distribution. So that's what comparability means. So that area has to be small. Okay? And itong RQ and R1 minus Q, remember, these are parameters, these are unknown, and given our data, we also have to estimate this parameter. So that adds a complication to the problem, the fact that we don't know their exact value. Okay, so I'll go to the slide number 4 here. Now, in MIELKE et al., they actually proposed a test for this. Proposed a hypothesis testing procedure for comparability, and ayan yung itsura ng null at saka alternative hypothesis that was proposed by MIELKE. And as you can see, the way that we are defining HO and HA here is really complicated. Just look at the form of HO and HA. We're used to testing, for instance, equality of means. We are used to testing HO mu1 equals mu2, o kaya HO sigma 1 equals sigma 2, or equality of proportions. But if you're testing something like this, it becomes really complicated. It's hard to work with. So all of those are parameters. Pati yung mga probabilities dyan, those are essentially parameters. Those are functions of unknown parameters as well. And so that becomes the challenge that I was initially presented with, where X and R and XT and X are here, at least we're assuming normality. So we have a model for the distribution of the test and also the reference product. So in MIELKE's hypothesis in HA, the HA here can also be written. If I just do the algebra here for HA, I can transfer the expression, itong expression in brackets, siya na lang yung isolate ko on one side of the inequality. So you can look at the equation below, or the inequality below. And then that expression in brackets has to be less than or equal to some quantity 2q minus c. Well, so in other words, we want it to be small. No, it's less than or equal to some constant, yung 2q minus c. And you might wonder, why not just combine that into one constant? Why specify a q and a c there? Well, they actually have physical interpretations. For instance, yung 2q is, kung mapapansin nyo, yung 2q is the area outside of the reference quantiles. Now, if you talk about the reference distribution, so that's already the amount, no, that's not inside the quality range. And c is called the equivalence margin. So c can actually be a negative number as long as what you have there is the right-hand side would still be positive, and it should not exceed 1. No, because we're talking about or exceed 2. But then 1 is already in fact very large here because we're talking about quality ranges. So c could be negative, and in the simulations, I will be choosing a negative value for c. Okay. So this is how the data would look like. We will be having measurements taken from the distribution of the test product, no, normal with mean mu t and variance sigma squared t. And we will also have measurements taken from the distribution of the reference product. And that is also the data set that MIELKE works with. And then yung sa kanya, yung ginagawa niyang test statistic, it looks like this. And oo nga naman, if you are checking your structure of your null and alternative hypothesis, the main highlight here is really the sum of those probabilities. No, itong dalawang probabilities na to, those are actually the red and the blue areas. No, those are what the probabilities represent. And we can add them because those are just mutually exclusive. No, these two events are mutually exclusive, so we can just add their probabilities. And so MIELKE essentially is just estimating those probabilities. That's the most logical way that you would move forward. If only this could work. But this is the first thing that you could think of. No, it's just a plug-in estimator. Just plug in your MLE for the mean. Plug in your sample standard deviation here. And this is what you would be getting there. And he works with W as the test statistic, but then the cutoff for W in order to ensure the correct type 1 error rate in his test is not really very well established. So that is one of the problems with MIELKE's hypothesis testing procedure. So X bar here, SR, these are just the customary sample mean and sample standard deviation of the reference product, and similarly for X bar T and ST. Now, there's one first problem with MIELKE's hypothesis. Now, again, I would need to go back to that part in order for me to explain what I'm talking about. There is already a mistake in how he writes his HO and HA because we know that the equality has to be in HO, right? Dapat nandito yung equality, wala sa HA. And the fact that this is a strict inequality here, that's already wrong. So that's the first thing. No, you have to fix that because that would mess up your calculations, so your evaluations for the test later on. So we have to transfer the inequality here, and also more than that, the procedure that he is doing, it doesn't really establish itong test power and size properties very well. But at least the paper by MIELKE et al., they raise a very appropriate, very relevant question, very important question on the comparability, and it just leaves us, at least it's well defined kung ano yung problem ngayon, and then we just hope to have an improvement for this, the way that the problem is being tackled. Now, in order to answer that question, how do you test for comparability, in order to propose a good test for that hypothesis that I showed just earlier, we will be resorting to what is known as fiducial inference. And this is not very well known, although this is a very old procedure. This dates back to the time of R.A. Fisher. He actually introduced this sometime in the 1930s. And what does fiducial inference do? Fiducial inference defines a distribution, a fiducial distribution for parameters that captures all data information about these parameters. In other words, it captures all of the information that your sample can provide. So it is a function of sufficient statistics, no, when you form its distribution. But then it's a distribution in terms of a parameter. So it borrows a Bayesian idea actually. Parang nagkakaroon ka ng parang posterior distributions of parameters mo, but it's a different approach. And the distribution can then be can be used in forming confidence sets, no, confidence intervals, or in general confidence sets for these parameters. And you can refer to the papers by Hanig. The one that I am quoting here is actually an expository paper, no, yung Hanig 2009, but then it was really this Jan Hanig who investigated, no, yung mga modern research on fiducial inference. He was really the one who was able to establish all of those properties, because for a long time, no, this was like long forgotten, and then recently it has made a resurgence. So people like Hanig are responsible for that, and also Samwi Rahandi, which I am also quoting here. Now, fiducial inference has recently made a resurgence under the guise of generalized inference. Now, kumbaga, there was a lot of papers, no, by this Samwi Rahandi, and that is really what triggered then itong fiducial inference, kasi napapakita natin that the generalized inference is actually just fiducial inference, just one type of fiducial inference. And what we Rahandi did, and we will also be using in this research, is the development of this generalized confidence interval. Now, generalized CIs are part of what is known as the generalized inference procedure, and we will be describing how we adopt it in the normal distribution, and we also following also the discussion of Krishnamurthy and Matthew. Okay, so here is just a one slide discussion on what generalized confidence intervals are, and then in the next slide, I will be showing how it will be applied to the specific problem that we have. Now, but in general, if you have a random sample, and suppose that we take a random sample from this distribution defined by that CDF there. Now, the CDF could be a function of parameters theta and delta, where theta is a scalar parameter that is of interest. This is what we are interested in. But the distribution could also be a function of a nuisance parameter. For instance, if you're just interested in making a inference about the mean, but the normal distribution also has variance as another parameter. Pero yung interest mo lang doon ay yung mean. So the variance is what's known as nuisance parameter. It's there, no, but you have to deal with it because it's there, but it's not the primary parameter of interest. So that's in general, you've got your theta and you've got your delta, which is a nuisance parameter. And a generalized confidence interval for theta is computed using the percentiles of what's known as a generalized pivotal quantity. Now, we're familiar with it. We're probably familiar with that pivotal quantity, or yung pivot natin when we form our confidence intervals. And we just have this generalized pivotal quantity where you have this quantity G. G is a random quantity. It's a function of big X here, which is a random vector representing the distribution of your random sample. And then your small x here for your data, and theta is the parameter of interest. So G is a function of big X, small x, and theta, and also possibly delta. No? But then G has to satisfy two critical properties. First of all, the distribution of this G is free of all unknown parameters. Now, so in that sense, it really is like a pivotal quantity. Its distribution is free of unknown parameters. It in itself could be a function of unknown parameters, but its distribution is not. And the observed value of G at small x, now if you plug in small x for big X there, you should get back your theta. So those are the two requirements for our GPQ. And we will be looking at specific examples for the normal distribution para mas maintindihan natin to. So I think it's still in the next slide. Now, once you already have this G, your generalized pivotal quantity, what's left for you to do is to take the quantiles of this G. Now, for instance, you can get the alpha over 2 and 1 minus alpha over 2 quantiles, and then that is actually a confidence interval or a generalized confidence interval for your parameter. So nagkakaroon ka ngayon ng inference para dun sa unknown parameter mo if you have this if you have that lower limit and upper limit formed by the quantiles of the distribution of G. And this study makes use of this approach. So we still have solutions. Solutions for GPQs can be found for the parameters now of the normal distribution. We can find this in the book by Krishnamurthy and Matthew. And those solutions that have been proposed, now we make use of them. We make use of that idea in forming our test for comparability. So again, ganito yung itsura ng data natin. We have a random sample of measurements from the test product, and we have a random sample of measurements from the reference product. So these are quality attributes, and we need to compute their summary statistics, yung X bar at saka yung S for both the test and the reference product. And ito na, no? These are the generalized pivotal quantities for our parameters that we will be using. So sabi natin kanina, there are two properties that GPQs will have to satisfy. First of all, their distribution should be free of any unknown parameter. And you can see this here for mu r tilde and mu t tilde, yung numerator dyan is standard normal. So it's normal 0, 1. It's not a function of any other parameter. And itong SR over sigma r, no, yung square dyan is just a multiple of a chi-square. So it is also not a function of any unknown parameter. And I think this one is even a, this is even a t, right? Or some constant multiple of a t distribution. So we don't have a problem here. No, we really know that its distribution is free of any unknown parameter. And the same thing with mu t tilde here. So its distribution there is free of any unknown parameter. And if you plug in yung small x for big X, and if you plug in also small s for big S, for both the reference and the test, you will get back your parameters mu r and mu t. So small xr plugged in for big xr, sorry, small x bar r would be plugged in for big x bar r, and small sr would be plugged in for big sr here. You will get back your mean for the reference product, and similar also for the test product. And we can represent it like this, no, yung mu r tilde and mu t tilde. Pwede natin i-represent sa ganito kasi alam na natin yung mga distributions in the numerator and the denominator. We could write it as zr ur. No, yung mu r tilde now can be expressed as x bar r minus zr over ur times sr over square root of nr. And similarly, mu t tilde can be written as x bar t minus zt over ut times small st, no, yung observed sample standard deviation for the test product divided by square root of nt, where this zr, ur, zt, and ut, very critical that all of them are mutually independent. So with that, we can sample independently from their distributions. Ayan. So below there, you can see where I'm presenting to you their distributions, that we can just sample repeatedly from those distributions and then form our pivotal quantities. Okay, now we also have pivotal quantities for our sigma r and sigma t. So ganyan. Also, yung distributions nila are free of any unknown parameter, and if you plug in small sr for big sr there, you will get back your parameter. So that one is kind of obvious, right? You see it na yung pag big S dyan, palitan ko lang ng small s, magka-cancel siya doon sa isang small s, babalik ka sa sigma squared r. And same thing for sigma squared t. And so we can write it in terms of below, na yung, in terms of the random variable that describes their distributions. So again, we are testing this problem, the hypothesis test. No, inayos natin ngayon yung HO at saka HA, the place where the inequality is found should be in HO. So we are just rewriting how we our specification of the null and alternative hypothesis. And this parameter here, pi, is the sum of pi 1 and pi 2, yung area above the area of the test distribution above the upper quantile of the reference product, and area of the test distribution below the lower quantile of the reference product. And those are the two probabilities here. And you can see that they are really functions of unknown parameters. So andyan yung mu r, andyan yung sigma r, They are functions of those parameters. So yung big Z Q dyan and big Z1 minus Q, those are just quantiles for a normal distribution. So those are constants. So all of those are really, pi1 and pi2 are both parameters. They're functions of unknown parameters. And again, we have a very complicated structure for our hypothesis testing problem, but hopefully we can appeal to those generalized inference procedure in order for us to form a test. And let's just investigate its properties later on. So yeah, now we can form the fiducial quantities pi1 tilde and pi2 tilde, where pi1 tilde and pi2 tilde are the quantities GPQs for pi1 and pi2. In order to form these GPQs, just substitute the generalized pivotal quantities for each of those unknown parameters like this. And then you get the sum of pi1 tilde and pi2 tilde, yun yung pi tilde natin. And then repeatedly draw from the distributions of ZR, ZT, UR, and UT, and then plug in those random draws into your fiducial quantities, and then you can form your quantiles. And so here is the algorithm in detail. Again, we are testing the hypothesis there, and we can draw from those distributions of Z and U for both the reference and the test product. And once we draw those random numbers, we can plug them into our GPQs for each of those parameters, and then we can take the 95th percentile of the computed pi tilde values, and we can reject the null hypothesis if the computed percentile is less than 2Q minus C. Now, whatever we specify here, our hypothesized value under HO. No, mag-reject na lang tayo ng HO if it satisfies this inequality. So how well is this performing? Well, when we evaluate hypothesis test, the type 1 error rate has to be correct, and it has to be a powerful test. So we will look into those. And in the simulations, you have to be careful when you're choosing your parameter settings, because you need to satisfy the boundary of the null hypothesis when you are doing type 1 error rate calculations. Kaya yung null hypothesis is quite complicated, as we saw, and so kailangan natin ng root solver in order to find the correct parameter settings to use. And well, in the second bullet, I'm already describing what those are. So sample sizes, I'm using 25 and 50. And the Q there is 0.05. Equivalence margin, just negative Q. I set mu R, the mean for the reference, to be 0. You can set any constant there, actually. I can let mu T vary from 0 to 1 and sigma R to be equal to 1. But then yung sigma T, that has to be determined from the boundary. I'm no longer free to choose any sigma T that I want. It has to be determined by the boundary of the null hypothesis. Kaya ayan, ito yung mga values ng sigma T. Baka magtaka kayo, bakit ganyan yung pinili kong values? That's just to satisfy boundary of HO in order for my type 1 error rate calculations to be correct. So those are those values. And then for the power also, I'm investigating power for different sample sizes and also some different values of the parameters. Now, these are just very limited parameter settings for now. And different values of sigma T, there's a reason why it's sigma T here that I am varying. Different values of sigma T represent varying amounts of the test distribution. But it represents the variability of the test distribution, which is our biosimilar. That's the one that we are introducing. So if we are developing it really well, then we want to have it just have small variability. Kaya that's the one that I'm varying here in the power calculations. Okay, and these are the results, and it's in the last two columns that you would see the type 1 error rate. And ideally, they have to be close to 0.05. So they can still be quite conservative, as you can see, nasa 0.02, and then they begin to get closer to 0.05 already for higher values of mu T, 0.038, 0.04. And we need larger sample sizes in order to ensure that we have better type 1 error rates there. Kailangan ng mataas na sample size. So this is some room for improvement. We can still do some calibration here in order for the type 1 error rate to be closer 0.05. So as of the moment, it's still a conservative test, no, except for when you have some certain values of the parameters when it can actually control the type 1 error rate better. And here are some power calculations. So on the x-axis here, I show you the standard deviation of the test product, no, yun yung sigma t. And remember, that's the one that I am varying. And the power function, habang lumalayo tayo, remember, if habang lumalayo tayo from the null hypothesis, the test is supposed to be more powerful. And as you go from right to left here, the standard deviation of the test product is actually decreasing. And that is why, and as sigma t decreases, we deviate more and more from the null hypothesis actually, and that is why the power goes up, no, to 1. No, aabot siya ng 1 for small values of sigma t, as we expect. No, the power function has to be monotone in sigma t. And I am doing it for 3 different sample sizes here. I'm doing it for 150 and 25 na sample size, and it goes up, no, as you increase the sample size, mas mabilis talaga yung pagpunta niya to 1, no, as we might expect. So these are 3 power curves here. And then that's it, no? So this comparability test again is used to assess the sameness of quality measurements of originators and biosimilars. And unfortunately, it involves a complicated structure of the null hypothesis, no? And it has to be. It's not just complicated because we want it to. It's really answering that question, no? How do you know if the distribution of your test product is within the quality range of the reference product? So hindi enough na mag-compare ka lang ng means. We are really talking about the entire distribution here. And frequentist methods might not be straightforward. And so existing methodologies do not have well-established size and power properties. And so what we are doing here is present a fiducial solution. The type 1 error rate can be controlled for some settings of the parameters, but not for all settings. So they can still be conservative in terms of type 1 error rate. But we can see that the power already goes to 1 as sigma t decreases. And also as you increase the sample size, then the test also becomes more powerful in that case. And just to introduce the kinds of research you can do in this area, especially for our graduate students here, there are interesting lines of research along this line. So in the in vitro dissolution profile comparison, parallelism in bioassay. These are topics that you might want to read about. Now, a dissolution profile, for instance, you have a drug, and then you are studying its amount of dissolution of also a test and a reference drug, and how do you compare those two? Parallelism in bioassays. So you might want to read about these ones. Determination of product overfill. We do this in product development. And what I just did today, comparability, similarity, and bioequivalence. In particular, itong comparability is what I focused on. And the last one is actually what I did when I was a graduate student. I did reference prediction tolerance interval estimation. And well, this also has applications in biopharmaceutical statistics. Okay, these are the references that I cited, just the ones that I cited in this talk. And well, if you wish to contact me, I'm giving you there my faculty email address. Okay, and that's the end of my talk. Thank you very much. So I will turn this over to you now, George.
Thank you, Sir Mike. Okay, so again, thank you very much, Professor Mike Lucagbo, for the insightful presentation. Our floor is now open for some questions. Okay, so again, you may use the raise hand feature of Zoom if you want to ask your questions live, or you can also message everyone or message me, okay, if you have a question. Okay, so let us give Dr. Lucagbo a warm round of applause.
Thank you.
Thank you, Sir Mike. Okay, any questions or clarifications, okay, from the audience? Okay, Sir Mike, I have here one question from a okay. So a participant raised his hand. So go ahead, Mr. Chan. You may ask your question live.
Yes, hello. Thanks, Dr. Lucagbo. Very interesting study that you have. Actually, I'm from UP University Health Service, so we're doing IT work there. But I'm also from DMME. I'm a materials engineer. So for my study in my master's before, what we did was analysis of variance actually. So we wanted to find the variance and then propose a model so that we would be able to um, find possible calculation for specific parameter. So we delved more on the variance analysis. So for your studies, I'm thinking it's more on the standard deviation, if ever. And I'm just curious if you could also apply this to this type of inferencing. Like I used JMP SAS software, and then I was like doing some graphs in Origin Pro. So for this type of study, could you actually also use statistical software for your analysis?
Okay, so this one, I think you can use any kind of software to apply the specific methodology that we are proposing here. Kasi this just involves generating random draws from the normal distribution and also from the chi-square distribution. So as long as your software can do that, no, kaya niya mag-generate galing sa mga distributions, so normal and chi-square, then yes, this is applicable. Of course, ano pa yon? That's of course, this is really new. No? So sa ngayon, hindi mo pa ito magagamitan ng software because this is a newly proposed. I haven't even sent it out for any publication yet. But then, so it's supposed to be easy, not to be implemented in any software.
Oh, okay, okay. I see, I see. Thanks for the answer, Dr. Kakbo.
Okay, Jeremiah. Thanks for the question.
Okay, thank you, Sir Mike, for the answer, and thank you, Mr. Chan, for the question. Again, okay, if you have questions or clarifications, you can raise your hand if you want to ask question live, or you can also submit your question via chat, okay, to me, okay, privately or to everyone. Okay, so I have here one question from participant, Sir Mike sent via chat. Okay, so why did you use fiducial inference and why not some other common methods of inference such as frequencies? I think nabanggit na kanina ni Sir Mike, why not frequencies? But another is Bayesian. Are they not applicable?
Okay, I'll first talk about yung frequentist. Well, there's no direct frequentist approach in order to answer this problem. There might be some bootstrap solution, and I also tried that out, and so far it's not very successful. Although I think now there is still some room for improvement. So siguro pwede if you do a bootstrap solution to that. But itong fiducial solution is a lot less complicated than the bootstrap solution. Now, as for the Bayesian, now we run into the usual problems. Now, what do you assume about your prior distribution for the parameters if you don't know anything? No, you don't have any prior information about your mean, you don't have any prior information about your variance or your standard deviation, then you run into that usual problem. But if you have a lot of information, then siguro pwedeng gamitan ng Bayesian inference. But as of the moment, I don't know if it can yield a lot of net benefits compared to the fiducial solution.
Okay, thank you very much, okay, Dr. Lucagbo. Other questions or clarification? Okay, so I think there's one question from the chat. Okay, do you already have any ideas on how to improve the type 1 error rate?
Okay, one idea that I have right now is calibration. So siguro if I can, so the idea of calibration is that you actually change the cutoff for the rejection of the null hypothesis. So as of the moment, we reject HO if pi tilde 0.95, the 95th quantile is less than 2Q minus C, yung presentation ko kanina. Now, the idea of calibration is that you can adjust the 0.95 there, change it to some other value, say 0.96, or it could be actually smaller, 0.94, depending on which one would control the type 1 error rate better. But that raises the question, anong pipiliin mo, 0.96 or 0.94 or 0.97 in order for you to control the type 1 error rate? In calibration, that is actually estimated, no, yung kung ano yung cutoff na gagamitin mo. That's part of the estimation. But that would have to be thought out really well. No? How exactly are you going to implement that? But that's the general idea there is calibration could address the problem of correcting the type 1 error rate.
Thank you very much, Dr. Lucagbo. Another question, okay, from a participant. Have you tried or applied this particular methodology to a real data set?
Wala pa po. No, so this is really new. It's mainly, no, I was motivated really to finish this. But I started this out when I was a graduate student before, and then for a long time I wasn't able to go back to it. But now that I was invited in this colloquium, I thought this would be a good topic, and so as of now, we just have simulations. We don't have any applications to real life data set yet.
Okay, thank you, Dr. Lucagbo.
I would welcome anybody, no, kung meron kayong data na similar ng ganito, send me an email and I would be happy to work on that.
Okay, thank you again, Dr. Lucagbo. We can accommodate, okay, one more question, okay. Okay, so there's another question from participant, okay. It's in Filipino, so I'll just read it as is. So meron po ba kayo naisip na pwedeng real data application? So like what type of, or siguro I think the structure of data or types of data na pwedeng pag-applyan, sir, nung methodology?
Okay, right now, I have constant meetings with a regulatory agency in the US. So I've been meeting with them almost on a weekly basis. And eventually, I might be able to apply it to a specific data set for a particular problem. But then a lot of the data that they use is actually confidential. So hindi ko alam, no, if that can happen anytime soon. I don't know in the Philippines if we have any regulatory data that is available for specific application. Of course, I could look up some data set out there, no, some existing already examples. Although hindi ko alam kung gaano yon ka-relevant, especially since meron ng mga decisions on whether the biosimilar has to be approved or not. So in short, I really have no concrete idea yet, no, of which particular data that I can use. That would be a good example. That would be a relevant example for this.
Okay, thank you very much, Sir Mike, for the answers. And of course, for those participants who submitted questions, thank you as well. So to show our appreciation to Professor Michael Daniel Lucagbo for his colloquium, on behalf of the UPSS Research Committee, may I present the Certificate of Appreciation. The University of the Philippines School of Statistics awards the Certificate of Appreciation to Dr. Michael Daniel C. Lucagbo in grateful recognition of his expertise and invaluable service as a speaker on Fiducial Inference in testing the comparability of originators and biosimilars as part of the UPSS Colloquium on the Statistical Sciences, given the second day of July 2020 via Zoom. Signed, Dr. Imogen F. Evidente, Director for Research of the UP School of Statistics, and Dr. Joseph Ryan G. Lansangan, Dean of the UP School of Statistics. Let's give Sir Mike a warm round of applause.
Thank you, George, and thank you also to the graduate students who helped now for today's colloquium, and thanks for all the participants.
Okay, thank you again, Sir Mike. So with that, I would like to thank you all for attending our colloquium on the Statistical Sciences. The link for the feedback form and the certificates of participation are shown on the screen. And this will also be shared via chat. So just wait for the link via chat. Okay, so again, thank you all for attending the colloquium on the statistical sciences. You can also subscribe to the UPSS mailing list to be updated on our future events and colloquia. Again, thank you and have a great weekend ahead.